Well, here's a short lecture on transformers. You know, transformers truly are more than meets the eye. I mean, because you can start with a car, it looks like it's just a car, but you know, with a little bit of imagination, it transforms into a crime-fighting machine. And actually, I don't really know what transformers are in that sense. The only thing I know about transformers has to do with power generation. In order to minimize I²R heat losses in transmission lines, it's common to transmit power at high voltage but low current, and then transform it to low voltage and higher current for your application. An ideal transformer changes the voltage without changes in the power. So we would have that in our primary, the current times the voltage, which is the power, is equal to our secondary power, the current times the voltage there. Now we note that if we have this configuration, that the voltage, according to Faraday's law, is equal to the negative number of turns times the magnetic flux that goes through the turns per time. But if this is a connected core here, then the voltage across the secondary output would be equal to the number of turns there times the change in flux, magnetic flux per time there. Well, in both these cases, the magnetic flux per time is going to be the same. So if we took the ratio of these two, we would find, getting rid of the change in magnetic flux per time, that the ratio of the voltage in the primary to the voltage of the secondary is equal to the ratio of the number of turns in the primary to the number of turns in the secondary. So V1 over V2 is equal to N1 over N2. The secondary current is going to be equal to the voltage of the secondary divided by the resistance of the load, whereas the primary current is going to be equal to the voltage of the primary divided by the equivalent resistance of the whole configuration. We're going to say that the power 1 is equal to power 2. Current I1, voltage 1 is equal to current I2, voltage 2. And we'll substitute in for our currents. V1 over our equivalent resistance of the circuit is equal to, times V1, is equal to the current I2, which is the voltage divided by the resistance of the load, times V2. Hence, we have V1 squared over R equivalent is equal to V2 squared over R load. But since we know V1 over V2 is equal to N1 over N2, we're going to substitute that in after a little bit of algebra. We get this. Our R equivalent for this circuit, looking into the circuit, is equal to the ratio of the turns, N1 over N2 squared, times the actual resistance of the load. This is the equivalent resistance of the load as viewed by the original primary circuit. So in quick summary, for an ideal transformer, we have that the ratio of turns N1 to N2 is equal to the voltage V1 over V2. In turn is equal to the reverse current I2 over I1 by the power formula, and that in turn is equal to the square root of R1 over R2, where R2 is the load resistance and R1 is the equivalent resistance as viewed from the primary. Let's try this out. Let's try a step-up transformer. A generator produces 10 amps root mean square of current at 400 volts. The voltage is stepped up to 4,500 volts by an ideal transformer and transmitted a long distance through a power line of total resistance 30 ohms. That will be our load resistance. Determine the percentage of power lost when the voltage is stepped up. Let's find out what we have here. Our original current is 10 amps. Looking in from the primary circuit, RMS. Our voltage in the primary circuit is 400 volts. Our voltage in the secondary circuit is 4,500 volts. And the resistance of our load of the secondary circuit is 30 ohms. From these values, we know that our power from the input is 10 amps RMS times 400 volts or 4,000 watts. That will also be the power on the secondary, because the power presumably is transformed equally. So the power lost in the line will be equal to the power of the load, which is also power in the secondary, divided by the voltage of the secondary, 4,500 volts. So our current in the secondary line is 0.89 amps, and hence our power lost will be that current, 0.89 amps squared, times the resistance of the load, 30 ohms, or 24 watts. So our percentage lost is 24 watts over our power of the circuit, 4,000 watts, times 100%, or 0.6%. Not a whole lot lost in the secondary line. What percentage of the original power would be lost in the transmission line if the voltage were not stepped up? If we had our original current. Well, if it were not stepped up, our original current was 10 amps RMS. That squared with a 30 ohm line would be 3,000 watts. And our percentage lost, 3,000 watts of the 4,000 watts would be 75%. So it's much better that we stepped up the voltage and transmit it that way at a lower current, so we didn't lose as much in the power line. Let's try another problem. A step-down transformer is used for recharging the batteries of portable devices such as tape players. The turns ratio inside the transformer is 13:1 and is used with 120 volt RMS household supply service. If the particular tape player draws 0.35 amps from the house outlet, what are the voltage supplied from the transformer? Well, the voltage RMS of the secondary is going to be equal to the turns ratio into the N1 of the voltage of the primary. That's going to be 1 to 13 of 120 volts, or 9.23 volts. What's the current supplied from the transformer? We can use the same ratios. I2 is going to equal I1, V1 over V2, since our power should have been the same between the primary and the secondaries. So I times the voltage should be the same. So we'll have 0.35 amps times 120 volts divided by 9.23 volts will be the current of the secondary, 4.55 amps. So how much power is delivered? We have 4.55 amps times 9.23 volts in our secondary. That is 42 watts delivered to the circuit. So that's a real short lecture on transformers. More than meets the eye.